All right, today we're going to decode the language of the universe itself. Seriously, it's this thing called thermodynamics, and it's basically the invisible rulebook that runs everything. I'm talking from the stars way up there down to the engine in your car. So yeah, let's dive right in. So let's kick things off with something you've probably used a million times. Ever really stop to think about how a thermos keeps your coffee piping hot or your water ice cold for hours on end? The answer? It's all thermodynamics, and it's actually, pretty brilliant. Okay, so at its heart, thermodynamics is really just the science of three big players. You've got heat, which is just energy on the move because of a temperature difference. Then there's work, which is the energy it takes to physically move something. And finally, the system. That's just the fancy word for whatever specific thing we're looking at.
All right, before we can even start to follow the energy, we have to draw a circle around what we're studying. We need to be super clear about what's in our little experiment and what's out. And that brings us to the first big idea, defining systems and their boundaries.
Okay, let's go back to that coffee. If we want to study how it cools down, the hot coffee itself, that's our system. Everything else, the mug, the desk, the air in the room, you name it, that's the surroundings. And that little invisible line where the coffee meets the air, that's the boundary. See? Not so bad, right?
Okay, now this is where it gets kind of cool. You can basically categorize any system just by asking what it lets across that boundary. Can actual stuff, mass get in and out? And can energy, like heat, get in and out? Just those two questions tell you pretty much everything you need to know. So this gives us three main types of systems. First up is the open system. Think of it like a revolving door. Mass and energy can just come and go as they please. Then you've got a closed system. Here, the mass is locked inside, but energy can still pass through the walls. And finally, the one we all want for our thermos, the isolated system. This is the fortress. In theory, nothing gets in and nothing gets out.
Let's make this real. A jet engine? That's a classic open system. It's constantly gulping in air and fuel and blasting out hot exhaust. Stuff in, stuff out. A sealed can of soda, that's a perfect closed system. The soda isn't going anywhere, but you can definitely make the can hot or cold, so energy is crossing that boundary. And our good old thermos, well, that's our best shot at making a truly isolated system.
All right, so we've got our system defined. We've drawn the circle. Now what? How do we actually describe what's going on inside that circle? Well, we need a way to measure it, like taking its vital signs. And in the world of thermodynamics, we call those vital signs properties. A property is exactly what it sounds like. It's just some characteristic of our system that we can measure. And we're talking about stuff you're already familiar with, things like its pressure, its temperature, or its volume. These are the key stats that tell us exactly what the system is like at any one moment.
And these properties, they basically come in two flavors. You've got intensive properties. These are the ones that don't care about how much stuff you have. Think about it. Temperature, pressure, those are the same whether you have a drop of water or a whole swimming pool. Then you have extensive properties. These guys are the opposite. They totally depend on the size or amount of stuff. Things like mass and volume are perfect examples.
And if you ever get stuck, here's a super easy mental trick to tell them apart. Just picture a room full of air. Now, in your mind, slice that room right down the middle. Ask yourself, is the temperature in each half the same as it was for the whole room? Yep, so temperature is intensive. Okay, now ask, is the volume the same? Nope, each half has half the volume, so volume is extensive. It's a little test that works every time.
So what's the big deal with all these properties? Well, here's the key. When you know all of them at one specific moment, you've defined the system's state. Think of it like a perfect snapshot in time. And if even one single property changes, the pressure goes up a tiny bit, the temperature drops, boom, you're in a new state. The snapshot has changed.
And this is where it gets really, really useful. There's this thing called the state principle, and it's a huge shortcut. It tells us we don't actually need to measure every single property to know the state. For a simple system, like say some gas in a box, you only need to know two independent, intensive ones, like its temperature and its pressure. Get those two and you can mathematically figure out all the rest. Pretty cool, right?
Okay, so we've got our system, and we can define its state, that snapshot. But in the real world, things don't just sit still. They change, and that change, that journey from one state to another, that's what we call a process.
Yeah, a process is just that whole journey from state A to state B. And all those little in-between states it passes through to get there, we call that the path. It's exactly like a road trip. You've got your starting point and your destination. The path is the exact route you drove to get there. Now, to make life easier for scientists and engineers, they often focus on special processes where one property stays the same the whole time. The key here is the prefix iso, which just means same. So an isothermal process, that happens at a constant temperature. Isobaric, constant pressure. Isochoric, you guessed it, constant volume. Think of them as the perfectly controlled experiments of thermodynamics.
Okay, let's talk about the ideal world versus the real world. In a perfect textbook world, every process would be reversible. That means you could go from state A to B and then go right back to A. And everything, the system, the surroundings, everything would be exactly as it was. No trace left behind. But you know where this is going. Here in the real world, that never happens. Every single process we actually encounter is irreversible.
So why is that? Well, the culprits are everywhere. You've got friction, which is always rubbing things the wrong way and turning useful energy into wasted heat. You've got turbulence, when things change too fast. And you've got that stubborn one-way street of heat flow. It only ever goes from hot to cold. These are the messy, real-world things that mean you can never really put the genie back in the bottle.
So, we've established that real-world processes are a one-way trip. But what's the engine driving them? What actually makes the energy move and causes these changes in the first place? Well, it all boils down to two ways energy can be transferred: heat and work, and one incredibly simple but powerful law that ties it all together.
So, whenever energy decides to cross that boundary we talked about, it can only do it in one of two forms. It's either heat, which is energy that's transferred just because there's a difference in temperature, or it's work, which is energy transferred when a force actually causes something to move, like a piston compressing a gas.
Now, to keep track of all this energy moving around, engineers use a really simple sign convention. Just think of the system as your bank account. Any energy that goes in is a deposit, so it's positive. Heat you add to the system, positive. Work you do on the system, also positive. And any energy that leaves is a withdrawal, so it's negative. Heat that escapes, negative. Work the system does on something else, that's negative too. Simple as that.
And finally, all of this rests on a law that's so basic, so fundamental, that when they discovered it, they had to go back and call it the zeroth law. Yeah, not the first, the zeroth. It sounds almost comically simple, but it's huge. All it says is this: if object A is at the same temperature as object C, and object B is also at the same temperature as C, then it means A and B have to be at the same temperature as each other. So, you might be thinking, why does something so obvious even need to be a law? Well, it's the entire reason a thermometer works. Think about it. The thermometer is object C. You stick it in your mouth, object A, and it reaches your temperature. Then you stick that same thermometer in a glass of water, object B. If it reads the same number, the zeroth law guarantees that you and the water are at the exact same temperature. Without this law, we'd have no reliable way to measure temperature at all. It's the foundation. And there you have it. That's the basic vocabulary, the building blocks for the language of energy. You now have this new lens to see the world through, a world of systems, states, and processes. So here's a little challenge for you. Just look around you, right now. What open, closed, and maybe even isolated systems can you spot? It's a fun way to see just how much thermodynamics is happening all around us. Thanks for joining me.